Morning everyone. We will continue with the polar plot. We have taken only some factors in the last presentation. So we will take the quadratic factor, either a quadratic pole or a quadratic zero. So we will see what happens when it is a quadratic pole. I have standardized the equation. So dividing by omega n square in the both denominator and numerator, I got the sinusoidal transfer function in this form. Now when omega equal to 0, the magnitude is 1 and angle is 0. When omega equal to infinity, magnitude is 0 and angle is minus 180. Now what happens when omega equal to omega n? So omega equal to omega n, this term will be 1, this term will be 1, but I'll get a j squared term, so it will be minus 1. This minus 1 and this plus 1 get cancelled, so I'll have 1 upon 2 theta j. So that will be the magnitude 1 upon 2 theta j, and the angle is minus 90 because I have a j term in the denominator, so the angle is minus 90. So again, when I am having larger values of omega, obviously the polar plot nature depends on the value of theta. So when I have larger values of theta, the polar plot will be a smaller one, and with the smaller value of theta, it will be a larger one because theta is in the denominator. Now for a quadratic pole, when it is 0, omega is 0, it is magnitude is 1 and angle 0. When it is infinity, magnitude is infinity and angle is 180. So it will be, starts at 1 when omega equal to 0 and angle is 180. So it will be like this. So these are some polar plots of symbol transfer function. When you have a pole at origin, that is 1 by s. When omega equal to 0, magnitude is infinity, and when omega equal to infinity, magnitude is 0 and the angle is always minus 90. Same way with a pole at 0 at origin and 1 by j omega square or 1 by s square. So what happens? I have double pole at origin. So when omega equal to 0, magnitude is infinity and angle is minus 180. So it will be so. And when omega equal to infinity, angle is, magnitude will be 0. Same way this also, you can do it yourself. Different functions, solve it. The transfer function is given, solve it and see whether you are getting. So here it is, standard second order pole and then pole at origin. So what happens when omega equal to 0? It is infinity and minus 90, and when it is infinity, magnitude is 0 and angle is minus 270. So this will be the nature. And when I have a symbol pole, two symbol poles, one symbol 0 and a pole at origin, what is the nature? Find out. Now finding the gain margin and phase margin from the polar plot. We have seen how to get the gain margin and phase margin from the Bode plot. How we will do? We have done the magnitude plot, we have taken the phase plot, and the point at which the magnitude plot crosses the 0 dB line, that is your gain crossover frequency, or the frequency at which the magnitude plot crosses 0 dB is the gain crossover frequency, and the point, you take it down on your phase plot, and this distance is your phase margin. So in this case your phase margin is positive, and to get the gain margin you take the point at which, or the omega at which, the phase plot crosses minus 180 degree line, and take the point or the distance between 0 dB and the magnitude plot, that is your gain margin. So in the first case both gain margin and phase margin are positive, so the system is stable. And in this case, this is my gain crossover frequency, this is the phase margin, so it is negative, and here it is, this is the phase crossover frequency, and this is the gain margin which is negative. So both gain margin, phase margin negative, so it is an unstable system. For stable system, both gain margin and phase margin should be positive. Now coming to the polar plot. This is polar plot plotted for some transfer function. What you have to do is make a circle of unity, because that corresponds to the magnitude passing through minus 1 plus j0. And I am having, why the point minus 1 plus j0 is important. The characteristic equation says that 1 plus gh equal to 0 or gshs equal to minus 1. When I take the magnitude, gshs equal to magnitude of gshs equal to 1. So that is why we are taking a unity circle. So the point at which the polar plot crosses minus 180, that is the phase crossover frequency or omega pc, and this is my 1 by kg is my gain margin, and (180 plus 5). You take the plot where it touches the unity circle, that is your gain crossover frequency, and draw a vector from 0 to that point, and the angle phi is the angle of gj omega at gain crossover frequency, and 180 plus that angle, that is your phase margin. So 180 plus this angle is minus, so 180 plus that angle will be a positive angle, which is this, that is your phase margin. So here the phase margin is positive, gain margin is positive, so the system is stable, whereas here gain margin is also negative, phase margin is also negative, because this is the phase of gj omega or open loop transfer function, which is some angle, negative angle above 180, and 180 plus that will give you a negative phase margin. So this gives you a unstable system. Now we will solve a problem. So this is the same problem which we did in the beginning for a simple quadrature pole. So which we have seen it as omega n, which we have seen, we discussed at that time. Now we'll solve a problem where my open loop transfer function is given. So I can calculate the magnitude and phase. Now at omega equal to 0, the magnitude is infinity and angle is minus 90. At omega equal to infinity, and magnitude is 0 and angle is minus 270. So This is a mistake here. It should be omega equal to 0. At omega equal to 0, the magnitude is infinity and angle is minus 90. So this point, it starts from somewhere from infinity, it starts. It crosses the minus 180, and at omega equal to infinity, the magnitude is 0 and angle is minus 270. So it comes like this. Here also it is omega equal to infinity. Here omega equal to 0 and here omega equal to infinity. Now at omega PC, the angle of open loop transfer function or GH will be equal to minus 180. So if I have to find the angle at omega PC, which is minus 180, and this is the angle expression of my transfer function given, minus 90 minus tan inverse omega PC minus tan inverse omega PC by 2. So solving, I get 90 equal to phi 1 plus phi 2, where phi 1 is tan inverse of omega PC and phi 2 is tan inverse of omega PC by 2. So taking tan on both sides, tan of 90 equal to tan of phi 1 plus phi 2, giving the trigonometric equation for that, I get tan of 90 is infinity, so the denominator will be equal to 0. From that I got omega PC as root 2. Now putting that value of omega PC in the magnitude equation, I got the magnitude as k by 6. Now depending on the value of k by 6, I can say the system is stable or not. The k by, that should be, magnitude should be equal, greater than, magnitude should be less than 1 for a stable system, because we know that 1 plus GSHS equal to 0. So k by 6 greater than 1, it is unstable. K by 6 equal to 1, marginally stable. K by 6 less than 1, it is stable. So it is k value between 0 and 6, it is stable. Thank you.